Reminds me of Tim's Apollo simulation. Nav, go. Weather, go. Capcom, go. Funny little story. We did like a little Apollo simulation. He was my astronaut. I accidentally killed him.
We have a countdown here. Yes, JD, go ahead.
4, 3, 2, 1.
All right. Welcome to our online audience and welcome to our in-person audience here in Bethesda, Maryland, just outside Washington, D.C. This is the February 2026 presentation of the National Capital Area Skeptics. I'm Scott Snell, the current president. As skeptics, we are known to ask tough questions. Often it's in the realm of far-out topics such as ESP or UFOs or claims that astronauts never visited the moon. But our curiosity extends into mainstream science as well. The National Capital Area Skeptics is, after all, a scientific membership organization that promotes critical thinking and scientific understanding. We champion critical thinking, information literacy, and scientific approaches to problem solving. The particular problem we'll discuss today is the difficulty of living and working on another world. And after the past couple of weeks of difficulty living and working on this planet, I think we're ready to take this on, huh? Those of you outside the Washington, D.C. area, we've just come out of a couple of weeks of living inside an ice cube. So it's my pleasure to introduce Dr. Caitlin Ahrens, an assistant research scientist at NASA Goddard Space Flight Center and the University of Maryland. She's part of the science team for the Lunar Reconnaissance Orbiter, LRO. By the way, full disclosure, I'm part of the engineering team for LRO. In particular, she uses LRO's lunar radiometer instrument to determine temperatures on the moon's surface. In collaboration with the Artemis exploration program, she serves as a technical support scientist to assist in risk assessments of astronaut, rover, and lander activity at the lunar surface. Dr. Ahrens is also Principal Investigator on a lunar surface sustainability research study funded in 2024 by the NASA Office of Technology, Policy, and Strategy. She's also a member of the American Society of Civil Engineers working on how lunar architecture should be monitored for hazards, including construction at the lunar surface. Today she's going to be presenting No Blueprint for the Moon, Navigating the Unknowns of Extraterrestrial Construction. Ladies and gentlemen, Dr. Ahrens.
Great, thank you for that introduction, and hello everybody. Yes, very exciting times for the moon. I know I've just spoken with some of you before this presentation about what is Artemis 2 looking like. It was just announced early this morning that we're delayed potentially yet again to April. So you know what, space is hard. So that's the way of it. So let's dive into other more challenging stuff as well though. When we get to the moon, now what, right? We keep talking about sustainability. We keep talking about building grand cities, either below surface or above surface. And what does it actually mean to live at the moon? But it's one thing to really, picture like it's our neighbor, it's close by, you only get there for a few days. How easy can it really be? Well, you know what? If Artemis is already giving us some answers there as just launching is hard enough, let alone even just trying to find somewhere to land. What are you going to do when you get there? There's so many different kinds of science you could do with the moon as well. So it's not just for the sake of, okay, we're going to go there, we're going to build a house, yippee. It's like, what are you going to do when you get there? What kind of housing are you even wanting there to begin with? And so I love showing this picture. This is from the Lunar Surface Innovation Consortium, ASCE. They have really beautiful different designs and concepts and everything though. But just by looking at this, like maybe your imaginations are starting to come into play here, like, oh, I wonder what that building could be, and look at the long stretch of hallways here, and maybe this is some like water tanks or maybe nuclear energies there. There's a launch pad up there. There's all sorts of stuff happening here. To a civil engineer, this is a nightmare. An absolute nightmare. And we'll be diving into like why it's nightmarish though. And while it's still very much exciting though, because we're already thinking about very large scale projects, but because it's so grand scale in this regard, we need to go back to basics though. We need to really go back to basics, that the fact that we haven't been back to the moon for over 50 years. How technology has certainly changed since then though. So as we're building, whether conceptually or hopefully physically in the next few decades though, is, you know, what is our even understanding of material science at the moon as well? Are we wanting to use local resources at the moon to cut down on cost and transportation? Yes, but what do those materials even look like, let alone interact with the lunar environment? What about AI construction? AI construction is starting to become a little bit more prevalent, at least in practice, for Earth construction type scenarios, especially when it comes to efficiency and like greenhouses. How does AI help with maybe different climate zones around the Earth and be more efficient in energy and thermal heat waste? Can we do that for the moon as well? Well, you know, let's maybe try to perfect it on Earth first before trying it out on the moon. And then what about propulsion systems too? You know, how are you going to store all of these resources? We're wanting to have nuclear waste on the moon at some point as a backup battery or even the main battery. What in the world is that even going to look like? How in the world are you going to even construct that on the moon, of all places though? So again, back to basics, right? We really need to know our foundations. And if I were to ask any of you like, okay, I'm going to task you guys to build a house. I'm pretty sure as you're thinking that through, are you thinking on like, oh, I want like a big house and I want an indoor pool and all this stuff. As you're thinking of just the architecture though, one of your main questions should be where, right? Everywhere, even around the Earth, is going to be different. Are you the mountain Alaskan type and you're going to have more of like the snowy background? Okay, now you need to be paying attention to your materials and something that's very cold, maybe permafrost. Something that's maybe a different type of temperature swings in Alaska. You know, what kind, are you on a hill? Are you on a slope? Are you near a mountain? So now you need to pay attention to your landslide hazards, and earthquakes happen in Alaska too. Or are you more of the sunny, beachy, tropical type? Okay, guess what? Sand is not exactly stable either. How close to the coast are you going to build? In which case, you need to be aware of tidal interactions close to your home. Are you going to be a little bit more inland? Like a smart person, please. But also your building materials are going to be different. You're not going to have sheet metal in the dry desert area. You're going to end up making yourself an oven. But then, you know, where does bricks lie in all this, or wood? Now, granted, we're not going to do like wood lodges on the moon for other practical reasons, though. But it still goes into show, yeah, sure, the moon doesn't have tropical beaches and Alaskan wilderness or anything like that, but you do have to be careful of your surface, your environment. What are you dealing with? There's still challenges here. So knowing the foundation, so what's the ground like? What do we even really know about just the plain surface of the moon? It's gray and grayer. Great. Okay, well, we got the color correct. Let's move on to then, like, you know, the actual physical beings of it, though. So we have probes. We've done samples with the Apollo astronauts. We've done core drilling. Yeah, I show the Mars rover here, though, but it kind of gives that essence of we've sent robotics to pick up samples, to look at these things. We've you know, certainly picked up rocks and meteorites as well. So we only have such a small sample size of what the moon actually is on a chemical level, even on a mineralogical level, but still not quite enough to really know about like how dense is it, how fluffy is it. Now, I've chatted with several astronauts in the past, and their best analogy for the lunar surface is flour. So you ever try to pick up flour? It's very dense, not garden flowers here, but like baking flour here. So it's very dense. You try to, you know, not to sound offensive here, pound flour kind of deal. It'll hurt, right? It's quite dense if packed. But then you try to get a scoop of it, and you even just try to breathe anywhere near it. You're trying to bake cookies or something, it'll go poof everywhere, right? The moon is pretty much the same deal. it's not as friendly as baking flour, and we'll get to that here in a moment. But even just sampling the moon and even across different planets, though, we've done a pretty good job of sampling. We know what to do when it comes to sampling. We've done this with astronauts, to drills, to aerogel. Aerogel is really fun. Think of it as like a jello substance, and it captures little tiny particles in this kind of jello-like substance. It's really fun. And drills and scoops and so on. So it's not like it's out of the realm of possibility of, oh, let's just get more samples. Yeah, well, you know what, we need to get there first. But yes, that's the idea. We want to get more samples from Artemis 3 and 4 and 5 and so on. That then can tell us a lot about our foundations, which can then lead to site planning. But then what instruments do we want to bring? And then how do we really become sustainable with this, though? So this is where our kind of to-do list for today is heading. So a little bit of moon facts here, though. So Lunar Reconnaissance Orbiter has really brought us a lot of data since 2009 when it got up there, and it's still going. How exciting is that? Yay! Yes, yes. Whew. As long as it's still up there, we're doing fine. But the thing is that with all this data, just years and years and years of data, we're still having questions, even just about the surface and the environment of the moon. So it's not just temperature and topography, and yeah, by all means, I'm a geologist. I'm gonna be fun here and be like, oh, how did this crater form? And the moon is full of volcanoes. Did you know that? There's some really fun volcanoes on the moon. They're really cute and squishy, and most of them turn up very blue colored or very red colored. Anyways, but in trying to combine all of these different data sets, and then including a lot of the Apollo temperature and probing into just one little tiny section of the ground there, then that starts to create a bit of a better picture here of, okay, now we've got some really heavy temperature swings in a lot of these places on the moon. So that's going to be an issue for engineers. We've got radiation like crazy, especially on the polar regions of the moon. That's going to be an issue for everybody. And so again, where all this is going is not just what science do you want to do, to then really hone in and localize all of this really cool science questions, though. How do we translate that over to risk, especially for engineers? So just some really pretty pictures that we're not just looking at the South Pole of the moon. Now, a lot of my examples later will be talking about the South Pole of the moon, so don't worry, we'll get to the really cool stuff there, literally. But thank you for laughing. But in essence, though, we are wanting to explore other parts of the moon. And so this is going to be with a program called CLIPS. So who has heard of the CLIPS program before? The two people over there. Okay, great. That's excellent there. So CLIPS, it's the Commercial Landing Payload Services. So NASA is wanting to bring about a lot of these interesting private companies coming into the fold here. There's some really exciting technologies that a lot of small businesses and tech startups are bringing into the fold here, going like, we have the skill sets, maybe we have the tools, we have the technology, we're just not feds. What do we do about this? We want to share, we want to go to the moon too. So NASA is allowing a ride share here. They're allowing a pretty decently sized landers and say, hey, you got a technology, write us a proposal, we'll hitch you a ride to the moon, and we'll figure it out. And then you negotiate where specifically you want to go to the moon. So now we get to test all sorts of different technologies and then share it. Because yes, the moon is all sorts of wild and crazy when it comes to geology. So maybe we get to sample a lot of the mare regions, the volcanic regions. We get to learn more about maybe these lava tubes. Are these lava tubes, even collapsed lava tubes, viable for subsurface habitats for humans and robotics? Cave systems. You know, if we are wanting to go deep underground because then it'll help with like radiation and everything, that's fine. That is a viable concept though. But we kind of need to know that these things are stable and safe to begin with. So how do we do that? Well, you know, there's a planetary caving has now become popular in the past few years. There's like a whole group that are actual cavers, spelunkers, crazy people, and they just love to look at space caves. And I'm like, good for you. Not me, you go. But still, we do need to know about the stability of these areas too. I'm going to put up a fun picture here. That's a pretty decent sized volcano area on the moon too. But how did it get made? What's the origin of those kind of volcanic systems? So from a scientific point of view, it's like we want to know how that came to be, what's there. But on the resource side of it, maybe even the engineering side of it, how do we sample it? Is this a resource? Maybe there could be radioactive elements near these volcanic places. Can we use that? How do we sample that? So it's a lot of back and forth with what I do between look at the pretty science and then what do we do about it? So to the south pole of the moon. So this is where we're going with Artemis 3 and Artemis 4. So not entirely sure what's going to happen after that, but we do know, at least with 3 and 4, we do want to sample more about the south pole of the moon. We've never been here before, ladies and gentlemen. This is some exciting stuff here. Now, granted, a lot of the moon pictures I just showed you, you're like, yeah, all right, look, it's more gray and more craters. Well, what could possibly be exciting than that? Well, I'll tell you, it's because you have areas here called permanently shadowed regions, or PSRs. So it takes the phrase where the sun don't shine to a literal state here. You have very deep, very steep, dark craters here that can house little tiny bits of molecules of water, carbon dioxide, and possibly other types of compounds as well, and then it freezes at the bottom of these craters. So there's a very good chance that there's frozen water all over the south pole of the moon. Now, why I say good chance here is because, again, we only have so much data, at least from LRO, from the polar regions, looking at the pretty data there, seeing how cold a lot of these spaces get. It can get as cold as Pluto. Think about that there for a moment. We're talking -400 some Fahrenheit. Bit nippy. And you may not feel so bad about the snowstorm a few weeks back. Think that the robotics and astronauts may have to endure a little bit of that. So stay cozy. But again, you might be also wondering, like, why? Just why? Why go there? But in essence, though, we do want to know more about this ice. From a scientific point of view, we really do want to know, like, where is it? How did it come to be? What kind of chemicals are there? What kind of data are we getting now? And is it still relevant? Most of the LRO data, remember, it's an orbiter. It's looking way up here. It can't give us really fine detail information until we get there and then sample it ourselves. But then once we get there, can we actually use it? Can we actually use the ice as a benefit or not? And if not, what do we do about it? Because then if it's everywhere, but it's not really resourceful, how do we either mitigate it or do we just deal with it? So like I was saying though, a lot of these PSRs though, on a scientific interest though, they could be quite old for cold trapping a lot of this water. Some of it goes through seasonal temperatures as well. I'm switching it over there. But there is some temperature variability here. So think of it this way, is that you're going from something that's really, really hot. I'm talking like way beyond Florida weather and then right into Pluto temperatures and then right back into Florida weather. That kind of variation just real quick in and out can really have some interesting effects with robotics. Now, when sampling these PSRs, we're more likely going to do it with robotics first out of safety. Whether we're going to do that with astronauts, that's still under debate right now, especially with suits, suit design. We really want to make sure that the suit designs are going to survive. Now, we're not going to just plunk them in the middle of the PSR and say good luck. It's going to take time for us to really figure out where we want to go all across the solar system, or solar system, South Pole, not solar system. Let's narrow it down. But even just looking at the different chemistries that can happen here as well, we're not just dealing with water ice, though. There's a chance that all of these can be mixed up in different variations and abundances all over the South Pole there. So anywhere that you see like blues and purples is where you would have something really, really cold here. So the warmer temperatures, you get your sodium and sulfur type volatiles, type ices to start freezing. That's actually quite warm. Water, methanol, and then you get some really, really fun exotic ices happening here though. These two, not good. Bad ice. They're very corrosive. It wouldn't be great. Now, back to, do we really know that they're there? No. It's purely modeling right now. There's a chance that they are there. We don't even know the physical state of this ice yet. So if anybody loves to get ice cubes in their drinks, like, are you a big ice cube person out of your freezer, or do you like the crushed ice? Right? Everybody has a preference. Or no ice, that's fine too. But for the moon, we have no idea. We don't know if it's giant ice cubes, more likely not. We don't know if it's crushed ice cubes, also more likely not. It's more likely going to be really tiny, really, really tiny in the void spaces of the grains of the regolith. But again, we don't know how deep it is. We don't know if it's in layers. We don't know how well mixed it is. It's more likely you're going to have CO2 and water over here, but maybe there's pockets of the sulfur over here. Could be spatially different. We don't know yet. So we have Viper. This is a very exciting rover to be coming up. It's had quite the journey. If anybody is familiar with Viper, if you are not, I highly recommend Googling what has happened to Viper for the past 3 years. It has had a little journey, but Viper is doing well and at the ready at some point. So Volatiles Investigating Polar Exploration Rover. Gotta love our acronyms, right? But the exciting part with Viper here, and why we call it a Viper, is it's gonna have a stinger here. It's a teeth. It's gonna have a really fun drill. It's gonna drill into that regolith, and what it's gonna do is that it's gonna heat up a little itty bitty laser into the hole it just made and essentially sniff up what it's lasering out of the soil and go, cool, that's hydrogen, that's oxygen, there's some neutron counts there, maybe there's some carbon in there. It's gonna give us our chemistry, yay, supposedly. But there's all sorts of chemical means here, mass spec, a camera system, make sure that we could actually see where we're drilling, which would be nice. Trident is the name of the drill system here. Also, mobility advancements. This is a very special system of a rover. Now, you might be wondering, like, what? It just looks like a rover. So what's so special about it? It's now the chassis and the wheel design is outfitted for steep slopes. Usually with rovers, we can't go usually above 10 to 12 degree slopes. This one is rated at 15 to 17 degrees. Perfect every time, hasn't slipped. And it's like, cool, all right. Excellent. We can go into those slightly deeper PSRs. So back to science themes, right? How does this then work for engineering then? I'll stop kind of giggling about all the cool science though, but from an environmental and civil engineering aspect though, how does this relate to site planning, to environmental hazard learning as well, and then eventually to sampling and construction? We got here, now we know what we're dealing with. What do we do? What do we do about it? So another good way to do about this though, through the meteorite samples and the core samples and all the rocks that the Apollo astronauts brought back, there's not enough for that to go around. Do you know how many engineers there are that really want a moon rock to play with? And even so, if you were like, pretty please, can I have a moon rock so I can test my instrument? Okay, here you go. Here's a rock. Oh, well, I got a big drill. What am I going to do with that? I don't know. Good luck. So what we have is simulant. So simulant is usually about between 90 to 98% accurate of fake moon dirt, essentially. You could also do fake Mars dirt. You could also do fake asteroid dirt. If anybody here is an educator, or you also just really want to play with moon dirt, there are dirt cheap ways to purchase this stuff for your classrooms as well. And museums and libraries love to play with this stuff too. Now, for engineering grade, there is an engineering grade where you could just buy it in bulk and just fill up a sandbox and you could test your rover capabilities. This is a way to test slip and slides for the rover wheels though. We create crash courses for them if you have to test camera movements as well, so we create little obstacle courses for them. It's fantastic. It's really, really fun to play with. I myself have played with it. But another exciting thing you can do with Simulant, can we 3D print it? Can we use this as a means to eventually 3D print on the moon and Mars? The answer is, we're not quite there yet. As with everything right now, we're not quite there yet. Now, this is a very, very interesting topic altogether though, but what essentially happens is you get your fake moon dirt, you gotta have some sort of polymer binder, almost like a glue of some sort. It's usually some sort of cement mixer. We try not to stick with water, you try to stick with a little bit more, more like glue-based products. So you make an ink, and then you gotta, what's called sintering it, so you heat it up real well, usually with some sort of very concentrated laser. You could also use microwaves, you can do UV. UV takes a while. But either way, you gotta sinter it, you gotta heat it up. It essentially bonds everything together, and then you gotta, cure it, wait for it to cure and everything. And then you can test out like the strength of it, how easy does it break, kind of deal. So this is still ongoing work for sure, and it's really quite exciting to see what has been 3D printed at what scale though. But most of this is really quite small. The scale part of these is only 500 microns, really tiny. I don't think you're gonna build a hammer or even a city with that anytime soon. So the technology is getting there though. That's the exciting part, is that we're already thinking about, wait a moment, if we can 3D print on the moon, that means we don't have to send up bags of cement to the moon every other month, assuming we can launch at all. And that's gonna cut down our transport, that's gonna cut down our mass limits as well, and so on. So where are we gonna build? So that goes into site planning. Again, what I asked you guys before, if you wanted to build a house, is it gonna be Alaska or is it gonna be in the tropics? When it comes to the moon though, we gotta think about all of these different environmental areas though, especially slopes. You kind of need somewhere fairly decent level, but there are ways to level the playing field, as it were. But what's your radiation like? You don't have an atmosphere at the moon, guys. Temperature. Your temperature swings through day and night. A day on the moon is 14 days. A nighttime on the moon is 14 days. It goes through 14-day cycles here. So very, very long, cold nights on the moon can happen here. Geophysical, there are landslides on the moon. There are micrometeorites pounding the surface every which way. And we still need to figure out how often that happens too. Illumination. If you're in the South Pole of the moon, you're dealing with shadowed areas. You don't actually have a lot of illuminated areas if you want your solar panels at all. You got your dust. Again, we'll get to dust here in a moment, and then regolith. How fluffy is your regolith? How strong is your regolith? You don't want to build something over a lava tube and then there goes your house. It just collapses right in. We need to know more about our environment. So very much open questions here as to, okay, we're building, what are some of the questions we're now thinking up? So like dust buildup, abrasion, adhesion, fatigue and loading. If you're having, you build your house on the moon, good job, okay. There's something called thermal fatigue where it goes through that day and night cycle, even very slowly. It's gonna build up some sort of fatigue. What happens to metal during the winter time and then right into summertime, right? Stuff is gonna either loosen or tighten kind of deal. If you do that enough times, even in and out of those PSRs, it's gonna create some level of fatigue. Loading properties, if we don't know how strong the floor is yet, and then you put a bunch of cement down, you don't want to collapse your structure already. And then volatiles, oh my goodness. So say if those little tiny pockets of ice are around your planning site, right? And you're like, it's fine, it's just ice, it'll sublimate away, no problem at all. Well, think of it this way though, if there's enough of that stuff around, you're drilling, you're building your house, it's gonna heat up. Yeah, sure, it's gonna sublimate everything. It could also make your ground much more porous as well. It's gonna make it much more fluffy and much more reason to go into the ground you go. So that's all to say there's still a lot of interesting open questions here, and we're gonna dive a little bit into hazards though. Natural versus induced. So this is a little bit what I do at NASA Goddard, is having fun with hazards and being the risk assessor for a lot of these stuff there. So again, I'll get to dust here in a moment though, but rock falls are actually quite common all over the place though, and they're really beautiful to see on the images. You can see how well they've bounced and skidded down these slopes and everything though, but the size of these boulders are pretty dang large, about the size of a small car with a lot of these boulders. You don't want to have your itty bitty rover at the bottom of a crater go, timber, here comes a rock, kind of deal. You know, they're not quite predictable just yet. There's still, there's still some like AI machine learning stuff happening right now with like rock fall detection right now, but what's that going to look like with exploration? We don't know yet. As I was saying earlier, with like temperature, with fatigue and so on though, but we're going to get into dust real quick. Dust can take hours to talk about though, but dust is the bane of our existence for lunar exploration though. Certainly for Mars exploration too. But lunar dust, not only is it tiny, it's unassuming, you can't see it. Not only is it tiny though, it's very sharp. So think of it this way though, when you're on Earth, you're at the beach, right? You get covered in sand, you just go like this, no problem at all. Just dust yourself off, right? On the moon, one, you have a helmet, so it's not like you go, can't do that. But we've also given the Apollo astronauts a brush. Go, here's a brush, use this. Okay, didn't work. Now what? I don't know, use a different brush. We had no idea what to do with this dust. It would just stick because that sand on the beach, beautiful beaches of Earth, you have wind and water. You have wind and water creating enough friction, almost like, think of it as like Play-Doh here, right? Enough friction, enough of those grains, it's gonna round out the grains. They're easy to dust off. On the moon, you have no wind, you have no flowing water, and you have essentially no erosion in this capacity. So there's no friction enough for these grains to smooth themselves out. These are all actually really quite talon sharp, tiny sharp little grains to the point where they will stick to metals, they'll stick to the suits, they can cut through the suits. We've seen this with Apollo. So especially joints, so knuckle joints, wrist joints, elbow joints, and behind the knees were the worst casualties as far as the Apollo suits went. This broke through the top layers of our Apollo astronaut suits just by rubbing, because you're working, right? Think of it, the next time you're like just turning on your car, how much your knuckles are bending, your elbows are bending, your knees are bending, right? Ow. But the thing is that even with dust, if they're sticking there, it's cutting right into it. So not only is it sticking to everything, now you're also scratching against everything. So all your helmets are starting to become visually impaired. Astronauts roaming around after only a few days, just roaming around on the moon. You can get some really heavy dust though. So dust on a natural level is already pretty dangerous. Let's go into induced. Let's just make it worse for ourselves now. We're just walking around. Apollo astronauts nearly lost some very critical batteries just by walking around. Okay, it's because they walked a little too close to their rover. We didn't know it at the time, but you just walking around, you're kicking up dust. Can't help it, it's very fluffy. And that dust It needs to go somewhere. It's lofted up and it's already charged. It's ready to go. It's statically charged. It's like rubbing a balloon against your hair and it's like, yes, I gotta land somewhere. A rover. Let's land over there. And then we got to pay attention to leaks and batteries and tools. You know, even the suits have to vent out CO2. That can't be helped, but it's still considered a small contaminant. So let's just rover around on the moon. Look at those rooster tails, right? That's gorgeous. Really quite pretty, except for the fact that, again, that dust will usually swoop back onto any kind of battery and solar cell systems on the back of that rover, and they got covered. Losing power efficiency like crazy. And you figure rubber will absolutely statically charge all these grains as well. So they gotta land somewhere. And so you already have a powered on electrically charged lander, a powered on electrically charged rover, and now you're electrically charging these grains. What could go wrong? They will stick to everything. Let alone that it's also a health hazard too. It can stick in your lungs. We've had astronauts have practically eye problems. It can have silicosis. It can certainly stick into your epidural layers as well. It's not pleasant. Don't recommend that. Now, another fun little city concept here. More stuff that we would need to be aware of if we were to have, say, greenhouses here or different, solar panels and whatnot. Now we need to be aware of like what's recycling going to look like for the moon. You know, any kind of closed loop systems like this is going to take time, especially when it comes to oxygen and we have greenhouses. Glass. What in the world is glass even going to do with those kind of temperature swings as well, especially if you have glass at what looks like glass and metal framing like that, and then you have those temperature swings? What might happen? Leaks. So all of this is to say, you know, even radiation, how thick is that glass? You're not just going to cook your plants right in there with all that radiation. Let's make sure that it's UV safe enough. But what is considered UV safe on the moon? We haven't tested that out yet. And then solar panels. This is going to get totally covered in dust. I have 100%. Any solar panels, it's going to need some sort of monitoring for dust as well, thermal fatigue. And by all means, mobility advancements is probably the nicest thing I put on this slide, though. But even so, as they're roving around, they need to be careful of how fast they go close to very sensitive materials. So are we going to need like speed limits near a lot of our habitats? Probably. You don't want to go. Everywhere is off-roading on the moon. That's not a problem. The issue is how fast it is. So sustainability, long-term habitats, okay. So what is really our current technology here? Right now, everything needs to be launched from Earth. So now we got to be paying attention to cost, mass, transport. But it all comes down to survival. We got to think about architecture in a survival sense, not in an aesthetic, make it pretty, have an indoor spa at the moon kind of deal. We don't have that kind of time or effort or even technology to even do that. There's no point. It's a survivalist mode right now. How do you make sure that we're efficient in our energy and our thermal and for sure, early habitats may certainly be subsurface. That's a whole different level of civil engineering tunneling headaches that we're going to have, but that may solve the radiation issue. That may not exactly solve the stability issue when you're digging far beneath the surface. So logistical, we got to be logistical about our design choices first, and then resupply. How do we store all of these supplies as well? We got to figure out not just living on the moon, what our own living habitats are going to look like, which you're going to need some level of like an outhouse, a kitchen, living quarters, sleeping quarters, a chemistry lab of some sort, which is going to cause a whole different headache and a half. but storage capabilities as well. Are you just going to leave your rover outside? Are you going to create a little rover mini garage in there? But emergency protocols. There's a fire in the kitchen. What do? Go outside. Okay, what are you going to do? Wait for responders to come in and deal with it? No. So emergency protocols, what has to get sealed off? Where's the problem? What kind of problem? These are the protocols that we got to work on right now for lunar architecture. Now for monitoring, again, love this this is my cup of tea. What kind of monitoring do we have on Earth already in place? These are the technologies we could put on the moon. Yay, we don't have to really do square run, rock bottom kind of technologies here. We know what to do. We know what kind of monitoring we need for like steel garages, pipelines. What happens with certain tunnels, with certain metals, and certain environments as well. Are you Alaskan pipeline, or are you something closer to the equator areas? Bridges and roads would have different load systems as well put in place. What do power plants and energy grids look like? What all of these would have is some sort of monitoring system to go, hey, I'm about to crack, I'm about to break down, help. And these are, the kind of systems, the kind of technology we're already aware of, we need to surely have in place for our moon habitats. So myself and a colleague of mine, Justin Hollander, up at Tufts University, Massachusetts, we just recently wrote a paper on structural health monitoring, applying Earth technologies. How can we apply this for the moon? And it's really quite similar that we can come up with, though. What kind of damage assessments can we get ready for these lunar habitats, no matter what the scenario may be? So this could include if you're near your launch pad. I don't like how close that launch pad is, by the way. That's my own personal bugaboo. There's a ton of stuff wrong with this picture, though, but I don't like how close that landing pad is. Granted, there's a berm here. It might be slightly slanted high enough to catch the dust and bring it back over, kind of deal. Look like a weird tidal wave kind of deal. But at any rate, though, not only are you going to have some sort of dust problem with your landing, though, but you're going to have a thermal and vibration coming off of this thing that's going to affect a wave of stuff happening here. You can have asymmetric loading with a lot of these walkways. So if you have like a heavy cart and you're trying to cart some, I don't know, moon bricks across your walkway, you better hope your walkway doesn't just sag every time you go across and make it to the next room. Just going from room A to room B might just be a survival tactic, let alone an escape room. I don't know. So different vibrational loads and walkways and so on. It could be an absolute mess. So we need to get ready for emergency protocols and that kind of monitoring. So that all goes into play as to what does sustainability really mean? And this is a term that NASA has brought about to the community really not too long ago, at least for lunar exploration, just to get a feel for, hey, lunar scientists, what does sustainability mean to you? It sounds like a really great essay question now that I said that out loud, like an SAT question, like, what does sustainability mean to you? The issue that we came up with, though, is that sustainability meant differently depending upon what kind of scientist and engineer you were. If you were an engineer and you heard sustainability, you want to make sure that your instrument is just going to keep running. So it's survival mode. It's going to keep running. Okay, is there a power off switch in case something goes wrong? You better hope there is. Good, that's sustainable in short term. But to a scientist, we're not really particularly interested in economical per se. We're more interested in like longevity, for sure, recycling, renewable resources kind of deal. But economically, reusing viable businesses kind of deal, maintaining those resources, all of this is going to get really mixed up in communication, and that's going to be a whole different challenge, is communication breakdown. Because if we don't get this logistically figured out now, it's going to be a mess down the road. And so right now, NASA is taking a really strong initiative right now as to not so much narrowing down the definition, because you don't want to get ourselves closed in a box. No engineer likes to get closed in a box. They like to think outside the box. We all like to think outside the box. But essentially really make it understandable for different levels as to what it means to be sustainable, because there are different definitions. There's different ways to explore the moon. And certainly there's other considerations too when it comes to architecture. So what kind of resources are even there? It's not just the ice, there's also different metals. Radiation and safety protocols, again with those emergency protocols too. We're wanting to build nuclear power plants on the moon. What happens if that leaks? You kind of need a monitoring system to let you know it's leaking in the first place. You also kind of need a protocol in there too. Geopolitical boundaries as well, and so on. So just a short shout out here for the Society of Risk Analysis, of which I'm a member of. We do have a small space sector subgroup though within the society. And so a lot of these open questions were still, hi.
I'm so sorry, we have another event and I have to grab some chairs. Can I roll those out? Do you have a
I'm almost done.
Okay, great.
Okay, okay, oh good. I swear I'm almost done. All right, and yeah, okay, so these are some of the questions that we're openly asking ourselves. Not to say that we're gonna solve these overnight, not to say we're even gonna solve these in the next decade, but at least we're thinking about these questions now, because we kind of need to happen with the what ifs. The what if this happens, do we have an answer? Do we have even an inkling or a concept of how to answer that? Because we know it may happen. Some of these, they're gonna happen. Single point failures, something's gonna break, all right? Even just building a simple rover shed, something's gonna break. You don't want it to collapse on your rover, but it might. But how do we know what to do when it does? And so on and so forth. So you get into like political and economics here, contamination policies as well, where, you know, humans are dirty, nasty beings. There's plenty of biology that could go wrong. What if our technology underperforms? What is NASA, let alone international entities, going to get ready to be ready for that? What if we underperform? At what point did we fail or stop short of and advance those technologies? It's certainly not going to be a one and done kind of journey here. So with that, I will now wrap it up and happy to take questions. But thank you all so much for having me chat about lunar architecture and civil engineering.
Thank you, Dr. Ahrens. And we do have some questions. But first, if we can help out our neighbors here.
Yes.
They're going to want to roll out this stack of chairs. And I hope that won't be a problem for this cable right here, JD.
Let's tape, yeah. There's a carpet there.
So they only need one of them. Well, let's find out. Those of you watching from everywhere in the world, is this thrilling or what? Jim Hawks is saving the day here for us. Former NOAA employee, National Oceanic and Atmospheric Administration. You had mentioned volcanoes earlier. I assume they're all extinct. Is that correct?
Yes, thankfully all the volcanoes are very much extinct. But the fun part then is they could all be different materials. And so that's where sampling can come into play, with a lot of them have more nickel, aluminum type minerals. Can we harvest, resource that, versus some of the older ones that may have more iron, magnesium type materials. So heavier metals.
I see. By the way, any idea how we could discover what the closest magma is to the surface? In other words, you know, there's still magma below the surface, but is there a way to, through seismology, I assume, to be like, oh, here's its closest approach to the surface of the moon?
a little bit of that. We need more seismometers, though, certainly. So if anybody's not aware, we have had seismometers back during Apollo era, but the thing about seismometers, you need multiple seismometers to really pinpoint what in the world is happening down below. If you only have just kind of one data point and go, look, it's a seismometer, it's vibrating, yay. Okay, good for it, but it's not going to give us the whole picture. There is going to be a suite of seismometers called the Farside Seismic Suite.
Yeah.
Coming about, CLIPS mission, yay. So that's going to be exciting for that, so more data points in that regard. There is a concept to have a lunar geophysical network, so have certainly around the South Pole. We don't know a lot about the tectonics of the South Pole. We do know that there's no volcanoes in the South Pole, which is interesting enough. But that doesn't necessarily exclude it from other tectonic anomalies on the moon. So like wrinkle ridges is a thing, graben, where you would have some sort of subsurface activity that would have magma of some sort, and then that magma just goes away, and then that surface goes, oh no, and collapses. I've been talking a lot about collapsing lately. I'm really selling the moon here.
Obviously, I'm getting ahead of the scientific data. These seismometers have not gone into place yet. Wouldn't that be exciting if it turns out, oh, there's this particular place on the moon where the magma is perhaps reachable by drilling or something? I'm getting too far ahead of things, but what are your thoughts about that wild speculation?
I mean, the easiest ways to get that kind of close enough to drill it safely and close enough would be lava tubes, because lava tubes would have already been either formed and or collapsed by surrounding lava pockets. So my guess on a safety level would go to lava tubes first. We already can see them.
Right.
As far as subsurface goes, we certainly need the seismometers. There are ways to do gravitational measurements from GRAIL, LRO, to give us hotspots as to like, ooh, there's like a thinning of crust here and a thickness of crust over here. Granted, their resolution size is like, here's a pixel. But you get a general idea of like the crust is thinner over here and it's thicker over here. Go toward the thinner crust. That's usually where you're going to get stuff closer to the surface. Now, from a safety aspect, that may not be so wise to drill too deep in, because what might happen? Yeah. It's the magic word today, guys.
Automating might be a safe thing. By the way, if people are online, want to Google this, you mentioned GRAIL, G-R-A-I-L. If people want to Google that, it's a gravity mapper for the moon. Very exciting gravitational field there, and good to know before we send humans to the surface again.
Exactly. And we had a question in the middle. You had a question?
Yeah.
Yes.
I was wondering, as I was watching the last few slides, to what extent redundancy might solve a lot of those things failing problems.
Exactly. Thank you for bringing up redundancy. Yes, so the thing about redundancy, we need redundancy for sure, because if you have like something failing over here, but your monitor's over there, it may not have time to realize, oh, there's a problem. So how much redundancy is enough is always the question, whether you're on Earth or on the moon. But also, how do you convince to take that amount of monitors? And so this is where it starts to get a little fun with, like, if they want to build a big city aspect. They want to build a big city in this regard, you're going to need a lot of systems. Now, the way to turn this into something profitable is that you would have redundancy systems short term to then get the data that we need to improve our materials, improve our building standards, improve our technical abilities to even monitor this stuff. Make it a way where we can know, oh, this is when this is going to give out. Almost like what is the warranty level of these materials? We don't know that yet. If we are redundant short term and really hone in on plaster these with monitors, but then able to learn that down the road long term, then we can start taking them off, because then we'll know. So I think redundancy is going to certainly be major for short term, but I think that's where it gets confusing in communication of like, well, redundancy is expensive and that's more sensors, and what does that even mean? Do we really need all these sensors? It's like short term, absolutely, because if you want to build this scale of anything, you're going to need redundancy. But then you use the word short term, then it starts to be like, oh, okay, we can get better. We can be better later. All right, hang on, guys. We had in the back there.
So yes, as you are showing, that location is also important, but the problem is that a lot of places that are providing habitable or habitual, if you want to pronounce it that way, areas may not be in proximity to the resources that they need to survive. So in addition to construction, how important is transportation, and how will that go in hand with the construction needs?
Yes, very good question. So for those of you who may not have been able to hear, though, it's just like location is one thing, but how does that relate to mobility, especially with resource management, for sure. So that goes into site planning for sure, especially with what are you going to do, what are you going to bring? Are you just bringing a drill, or are you bringing a backhoe? Because that's going to really affect your mobility there. And I kid you not, there are groups out there that would love to bring their backhoe up to the moon. There are companies out there that are at the ready, and I'm just like, I kind of want to see that happen. But also, no, not yet. We're not ready for this yet. Let's hold off on a bit here. But as you're planning this out, like slopes, so what's your mobility capability? Are you like tiny rover, you grab a few rocks and it's like a little red rover wagon, red flyer wagon kind of thing, go put your rocks in there? Or are you dealing with like Perseverance, SUV-sized rover capabilities? Those are much thicker tires. They could probably deal with a little bit steeper slopes. Then, are you even wanting to go to those shadowed areas? Maybe not. Maybe you don't actually need to deal with that kind of the icy bits of the South Pole, only if you really need to and want to as well. Right now we're focused on how do we get to the ice, how do we sample it, is it a viable resource? Because that's a huge question we don't know yet, is it even viable? And there's huge debates on that as to like, probably not, and maybe to some extent, but then what happens if it gets depleted? That's a whole different protocol as well. You get there, hey guys, we found ice, hooray. Oops, so never mind, we used it all up in under 10 years. What now? And I mean, there's concepts of like, maybe we can like closed loop recycle this kind of ice. Maybe we can make our own ice on the moon, which might end up being a contamination issue all in itself. But if it means for survival, maybe not. There's a debate there.
Yes,
Yes.
I also want to get on the specific. I was talking about more of a grand scheme of things with analogs on Earth. For example, like cargo ships, rail lines, oil pipelines. Is that something you can foresee needing to be planned? How can be constructed and maintained?
Oh, gotcha. So it's a much grander scale. Okay. So probably not. I don't want to get in the pipelines. But probably not in the sense of oil pipelines, because there would be no oil per se. But how do you transport nuclear power energy to your other sites? So are we going to need power grids? Yes. But solar power is very, very limited on the South Pole. It's great everywhere else. Equatorial regions, sun all day, at least for 14 days. So we got to be very picky when it comes to the South Pole for energy resources. For mineral resources, it's not so bad. For ice resources, we're fine. But energy resources at the South Pole of the Moon is going to be a nightmare if we're wanting to do anything solar related. Nuclear though, ugh, now you're going to have an issue of placement for sure. Because if you plunk it in the middle of a crater, you need to choose the right crater that you know how to access it correctly. And then where are you going to plant yourself to access that energy? And it can get a little wild for sure. And then especially who can benefit from it too. So I don't want to get too much into the geopolitical aspects of it though, but if we own the nuclear energy, who do we share it with? And or can anybody else tap it? Tap in and out of it, who knows?
So that just touched on to my question.
Yes.
This is NASA project,
Mhm.
US, but the moon isn't our toy. So, you know, are we at this stage cooperating with scientists in other parts of the world, or are we acting like it's our toy?
Well,
Caitlin, would
Yes.
you restate the question?
oh, yes, sorry. So restating the question here, the US going full forward with, you know, certainly with Artemis and other activities, the moon is not our personal toy, but what does this mean for international cooperation and colleagues and entities as well? So I'm going to let you make your own opinions with what I'm about to say. So we do have something called the Artemis Accords. We have, I believe we're over 50 countries signed on the Accords right now. So different countries that abide by, it's not rules per se, it's more like morality, if anything, of like, hey, guys, the moon it needs to be a shared resource. This is, you know, somewhat taking on the role of what the United Nations tried to do with different space agreements and the Moon Treaty. We've learned our lessons with what happened with Antarctica treaties as well. We're kind of taking a lot of notes from that treaty because Antarctica is very much shared among different nations as well. But for the moon, it's much larger and pretty much a much grander problem. So you have the Artemis Accords. However, Russia and China have made their own separate accord, not with US, nor have they signed the Artemis Accords. So what does this mean going forward? So the only thing going for everybody right now is through the United Nations, there's got to be a level of communication. If you're going to launch, you've got to tell the world. What you do on the surface, not our problem, that's yours. How do you interact with others? Not our problem. You at least stated that you were going to go to the moon. You're off-world, not our problem. Now, NASA does have ways that have been agreed upon by other countries as well, where you would have areas, I don't remember the exact distance of these safety zones, but the Apollo 11 site and the Apollo 17 site specifically have safety zones around them that no one can go near these sites at a certain distance because that would cause historical interference. That has been agreed upon. Okay. What interference means everywhere else, that's a protocol we do not have yet. This is where that communication breakdown can happen. So Artemis Accords is very much like, hey, everybody, if you signed on to our club, please let us know what kind of activities you want to do. Let us know how we can help and collaborate. Yay. Just be nice. And that's pretty much it with the Artemis Accords. It's more a positive morale of communication. But in practice, no idea yet. Now, if you're interested in like the geopolitical aspect of, hey, we built something on the moon, now what? I myself and a colleague of mine from the Czech Republic have just recently published a paper in the journal Space Policy, where we give the case scenario of building a moon road. what does that mean then of who owns the road now? Who's allowed to use it? Who's going to be in charge of the maintenance of these roads? You're going to have moon potholes. Okay, the moon's already full of potholes. Let's add more. But it still goes into who's responsible, especially if you're having different international entities even nearby. Say if it, like you got the US and then you got Argentina over here and then you got maybe the Czech Republic, the Italian Space Agency. We'll do it with the Italians over here. You have a road going through. They'll all benefit from the road. But what if this road over here starts to break down more than those? Is the Italians now responsible for their section of road because they're closer? That needs to be agreed upon. And then monitoring and so on. It's almost like adopt a highway but for the moon. But still, if you're interested in reading that, it just got published though, it's online, if you're interested in that regard. So yes, these are questions that we're still very much doing a lot of the what ifs, because these are the what ifs that we need to start figuring out now. Again, it's going to happen. What are we going to do about it? Yes.
I've been exploring a lot of the stuff in fiction about that involve going back to the moon. I'm not sure if you're familiar with that. Alan Smale, who used to be a Goddard scientist, wrote it's now up to 3 books, a fictionalized history of the Apollo program, where we actually continued going to the moon. He has structures being built and interesting ways to get there. But yeah, I think the first part of the series is called Hot Moon. And but it's really fascinating. He's got a 3rd one out that our group hasn't read it yet. But there's a lot of that kind of stuff in there. And just recently I rewatched 2001: A Space Odyssey, which has that great scene where they're going to the moon and landing at Clavius. So anyway, but yeah, great talk. Thank you.
Thank you. As far as like other book recommendations go, there's a book called from Alan Steele. I'm really trying to remember the title of the book. Ugh. And it's escaping me, but it goes through moon miners unionizing and what does that look like going forward. And so a union, the workers are being mistreated. How do they unionize? What does this look like for management that is stuck on Earth? And so communication breaks down, and what do worker optimization, you know, they're treated as like, you need to do the work. You need to be efficient for your world, but their benefits aren't so great. And so it's a really fascinating book, and I apologize, I cannot remember it, but Alan Steele. The what?
The Tranquility Alternative?
No, is that from Alan Steele though? Okay, that might be the prequel.
Andy Weir also wrote a book about a colony on the moon also, where
Yes.
I think they visit.
That's his 2nd book. That's
Yeah,
after
second
The
book,
Martian.
Yeah.
Yeah. So that book,
I think it was Artemis or something like that.
I think so as well, yeah. That book got a little interesting. It's not too much on the lunar science side of things. I was a little disappointed in that though, but it still got into a lot of transport problems in that book. And so that was interesting to read through, like, oh, yeah, that's gonna break down, more likely.
By the way, Alan Smale's name was mentioned as this author. He's also a fine vocalist with an a cappella group called the Chromatics. So I'm just putting a little plug in for the Chromatics.
Also, I think presenting at AwesomeCon in a few weeks.
In Washington, D.C.'s AwesomeCon is going to have the Chromatics perform. A quick comment, you mentioned Czech Republic. Czechia, for those of us who have been watching the Winter Olympics, that's their rebranding, I guess. Yes.
So this is more or less a 2-part question, with the second one depending on your answer for the first. So with all of this construction for basically trying to live on the moon, at what point do we cross the line of trying to go from surviving on the moon to terraforming it?
Okay. So question of terraforming, we're certainly not ready, nor is that really in any plan book right now. It's certainly always something to think about, especially for Mars as well. How do you terraform Mars? It would have had, there's still salty lakes, even underground lakes on Mars, certainly nothing like that on the moon. But the issue with like any sort of terraforming, it's almost like the definition of sustainability. It means something different for different people. So terraforming to a scientist is like fingernails against a chalkboard to us. But to engineers, it's probably also a headache to engineers as well, because then you're dealing with different materials and propulsion and trying to have a sustainable atmosphere, and what does that even look like? So as far as terraforming goes, as far as exploration, no, not particularly. At least we're not concerned about it right now. It's more, let's survive there first. Even short term, we need to figure that out now. So short term surviving, and then we thrive.
With that said, I'd like to see your opinion on the ironic situation of considering terraforming is that when you look at a history of humanity, what we are known for being good at is de-terraforming Earth. So if we're going to put an effort into doing such things on other planetary bodies, would it make an ideal sense to use that magical technology on this planet first, because it really needs it?
Yes, absolutely. So this is where a lot of fun technology can happen for the moon before we even get to Mars. But we have had several instances through NASA's history, certainly since 1958, where certain technologies that NASA has developed on the Skylab, International Space Station, even with Apollo astronauts, just solely for maybe a specific purpose, and go, hey, that worked. Let's develop it for like the mass population. We have had histories of that. So that's not out of the realm of fantasy and imagination there, that if we developed a certain technology, take for example, a really good example here, dust is a problem on the moon. I said that several million times to you guys. If we solved a dust mitigation technology for the moon, can we use that for Africa? Can we use that for dust mitigation populations that get choked out with their agriculture by dust storms? Can we then reverse that kind of technology? Absolutely. Or recycling water systems. We know that the water is very finite on the moon. If we know how to replenish it, maybe even make more. Can we use that for desert areas? Maybe even out in Arizona and New Mexico, and replenish water there. So absolutely, those kind of technologies, yes, but we need to develop them first. But whether those get tested on the moon first and then right back to us, yes, I'm all for it, absolutely. But it needs to work first. That's always the gamble.
I'm curious about the slide you showed of the permanently shadowed regions. It looks like a time-lapse photography.
Yeah, it's very quick.
What is the, it is in fact a series of genuine images, or is this?
Nope, yep, that was a series of images, yes.
Okay. And over what duration roughly?
I think that particular duration would have had to have been on the order of days sped up, because shadows do move quite slowly, very slowly.
Right. Of course, as you said, the cycle would be a month to get back to the same place in terms of the moon going around Earth and the sunlight.
Oh, right.
Yes.
Okay, yeah, if you're wanting a specific phase to orbit, at least to the South Pole, and get a certain action shot.
Yeah, by the way, you had mentioned, quote, seasonal temperatures, and people may be surprised to hear that
Yes,
the moon has seasons.
Yes. Now, I'm not saying seasons in the sense of, look, the crater is orange, it must be autumn. Nothing like that, thankfully. But no, it does do what we call summer and winter. So not exciting, not exotic. We don't give them fancy names or anything.
Sun angle.
Exactly. So
Right.
the more sun you have, it's summer in the South Pole, and then winter in the North Pole, and vice versa. Equatorially, you're hot and hot. I mean, it's Florida, but with South Poles, yes, you do get winter where the sun is so low, it's like barely a speck above the horizon during winter time, and you have many long shadows, really, really cold temperatures. I mean, when I said temperatures as cold as Pluto, those areas of cold expand during the winter. Then they lessen up in the summer and so on. But because of that dynamic, we're still learning what's happening to the ice during that kind of variability.
Right.
We don't know.
I assume Artemis 3 and 4 are planning to land during southern summer. Is that correct?
Yes, yes, very much. It's more likely that we're going to get more sunlight for our
Right.
communications and power systems and everything like that. So yes, we are targeting lunar summer, or at least at the very least late spring kind of deal. But in essence, yes, for safety reasons, for power systems, yes, go for full sun. Now, as far as how do you sample ice when it's summer? Artemis 3 is more likely not going to even touch the ice yet. We want to truly know what we're doing after 50 plus years of not being on the moon.
Right.
We just need boots back on the ground, take a few samples, come back home, okay.
Yep.
Do a few drills, yay. It's still going to be exciting, don't get me wrong, guys. Artemis 3 is going to be really, really exciting, just safely basic. Safely basic, nice and easy. Well, no, I shouldn't even say that. It'll be nice.
Caitlin?
And challenging, but with Artemis 4, we are hoping to get the technology ready to grab the ice, which, let me say real quick, just how challenging this may be, right? Okay, get ready. So, we're an astronaut, right? Get ready with the camera here. I'm going to be moving around. Okay, you have a metal container. You're going to get something that is cold as Pluto into the container. Where do you put it? You're not going to hold it with your hands. You got to put it in a freezer on the rover, which conducts heat, which also needs to conduct enough power to keep that freezer going. Okay, now rover over to your payload system. Put it onto your rocket with another freezer, which also needs to power that freezer to keep it cold. Okay, now you launch up from the moon, go back to Earth through a screaming hot atmosphere of the Earth, land, and then transport it into a truck to then go to a laboratory and then chuck it into a laboratory with a freezer, all while trying to keep it cold. No problem, yeah, sure.
While you
Yeah, remember I was talking about single point failures? We need the redundancy for sure, especially with just that one ice sample that we've never done before, which is going to be exciting all of its own. But man, what a journey that little piece of ice is going to take. So yeah, are we expecting loss of science, which is where you're going to have some level of contamination or some level of losing ice? It's going to sublimate in the container. Yes, we actually are very much ready to prepare for those kinds of consequences. How much of that consequence, we don't know yet, but we are very much aware it's a risk. It's an inherent risk. Something's going to break. But that's where we can learn all the lessons learned of even just that simple picking up and packing it and then chucking it to a lab. So many things could go wrong. We know something's going to get lost as far as the science goes. And at what point, even just our container system, even the architecture of the container right now, it's so fascinating to be in, well, I shouldn't say fascinating to be in Teams meetings for hours on end talking about a container. But here we are. But I will say though, even just talking about what kind of metal you're going to have, that's not going to interfere with the ice either, or even corrode the insides of your container. That would be bad. And the sealant and everything, and then how tall or how short this container is going to be. Oh my goodness, we're still talking about it. It's going to be fine.
I think in the long term, though, ideally you'll have your lab on the lunar surface so that you bring your sample right over to this little base, your scientific outpost, sort of like Antarctica, but on the moon, and you do your work there.
Yes.
That would be the long
So
term.
that is definitely the goal, is to have a lab on the moon and then you don't have to bring it back. But while bringing it back, so the University of Alabama, Birmingham, did win a NASA contract to work on that freezer system. Not for the moon freezer system, but for a lab freezer system to bring those ice samples in. So that's going to be some exciting work coming up with University of Alabama. They just got awarded maybe like just last month, so very, very new award for them. It's several years worth of a headache and a half for them, so good luck to them.
Would you say a word about your research? You're involved with an instrument on the Lunar Reconnaissance Orbiter. It's a radiometer called Diviner.
Yes.
And so I assume you're doing thermal related research on the surface of the moon. Would you say a word or two about that?
Sure. I'm gonna try to find. Whoops. I'm gonna try to find that particular slide. I could also help, and while I'm finding the slide, I can answer your question, sir.
Well, I was going to ask what Scott just asked about the analysis on the moon before it gets put. It's irrelevant because I was trying to ask what you asked about analysis prior to putting it in the beer cooler.
That's a fantastic analogy for that. Absolutely. If we have if Igloo then becomes the company to build a cooler for the rover, just pop it in.
I think it'll be Yeti. It'll be Yeti.
Yeti? Oh, okay, so the race is on between Igloo and Yeti. I am all for it. Please let that be a thing. But see, this is where companies can then come in and go hey, we have the technology. Do you need a refrigeration or a freezer system for your rover? Call us. Okay, so yes, back to Diviner. So this is our lovely Diviner. I wish the moon was this rainbow colored. It is not. But yes, looking at all of these different things, this is only a snapshot in time. So Diviner has been going around certainly since 2009. It stopped going to the poles around 2015, 2016, right? So how the LRO orbit goes, though, is that it used to go polar to polar, and then as the spacecraft is moving in its orbit, it's starting to be like a little spinny top kind of deal. It's now at an angle, so it's no longer at polar region anymore. So what we have is what we got. It's from 2009 to 2015, and that's it. So we don't have any updated thermal maps right now on the moon. But what we do have is at least seasons. We can see that summer, winter scenarios between the different years. I can zone in on a lot of these craters and go, okay, Amundsen crater here has some really wild summer winter variations here. I feel like a weather reporter now. Over here at Amundsen in the next week, we're gonna have some cold drafting happening inner crater side. And then let's look over here at Hayworth now. So Hayworth here is going to be about 70 Kelvin through the week. It's probably going to drop down to 60 Kelvin by the end of the weekend, though. Now, can we get to this level of weather forecasting? Not yet, but that is going to be certainly a fun thing to do in the future with certainly more updated thermal mapping, though. Now, do we want to do, say, weather forecasting on Mars? Yes, absolutely. So there's a team at Goddard Space Flight Center that is already on the works for that, though. But for thermal awareness, we're still working on it.
We're having a very interesting thermal event coming up in 2 weeks when the moon passes through Earth's shadow. So here in the Washington, D.C. area, it's going to be the night of March 2nd, 3rd, and close to sunrise is when the center of the eclipse occurs. So we're going to see the setting eclipsed moon, and on the other side of the sky, the rising sun. And as many people probably already know, that reddish color that you see on the moon during an eclipse is every sunrise and sunset light projected onto the moon. So the Washington, D.C. area and everything in the sunrise zone is going to be part of the light show, right? Our atmosphere is going to have its light projected on the moon. And so anyway, March 2nd, 3rd, the totality, just before sunrise. Oh, we have a weather forecast or a psychic forecast by our producer that it will be cloudy. Sorry, great.
I mean, yes, more likely.
A lot of what you were describing in terms of what they have to worry about with construction, there's a computer game called Astroneer where you actually go to, you have I think about 5 or 6 different planets. They're all, the ecosystems on these planets are fascinating, but you have to build stuff using local resources. But I keep wondering, suppose you actually ported some changes to that for an actual more realistic environment. Because you have to be, you're an astronaut, you're there, you have to first build a little 3D printer out of local resources, then you use that to build other things, and then build a larger 3D printer. It's pretty, I've gotten addicted to it, but anyway, I just thought I'd throw that in there because it's something to play with these types of ideas and what kinds of projects. You have one planet that's basically an ice planet, there's another one that's like Mars, there's another one that's like Earth, and you have to, go around looking for resources and stuff like that. But anyway,
That's a fun thing. I'm going to have to look that up.
yeah,
Oh my goodness.
I'm addicted to it. Thank you.
But that kind of stems into something else too. So during introductions, is that I'm a PI of a lunar sustainability project, and my lovely co-I over there as well is here in the room. So our team is actually figuring out what does decision making look like though. So like with a game, right? You're given a scenario. Do you go this way or this way, right? It's almost like a choose your own adventure, but with with much construction level type stuff. But for decision making on the moon, we need to be aware, like, yeah, everything is going to go wrong at some point in redundancy and so on. But at what point do you need to shift your objective or shift your technology? Are you shifting because of economic and political reasons? Are you shifting because your technology failed to meet your objective? Now you got to completely redo it. Again, everything could go wrong. How do decisions get made? So we were funded by NASA to have this decision framework, which was already established by the USGS, actually. So we collaborated with the USGS on their decision framework. Funny enough, with fish management, that's a whole separate story there. But we ran essentially scenario models using this USGS framework. We essentially replaced fish with astronaut. And I kid you not, this is pretty much how the conversation went. But it worked because there's so many different decisions that can pretty much overwhelm the system. And especially if you are the one making the decision, you're going to get overwhelmed with 1,000 decisions. And even just doing nothing is a decision, but you're not going to, that can't always be the answer either. And so what does a decision framework even look like? So our team has been working very hard for the past year. We're going to get some exciting papers coming out. NASA still wants us to continue our work as well, maybe have it as almost like a training thing as well for future program managers as well, because they're the ones that are going to make the decisions, not us scientists, not us engineers either. It's those program managers that are going to have to be like, hey, at what point are we shifting or are we on track? But how do they know?
I Googled your research on this topic. RAD, resist, accept, direct. If
yes.
people want to
You did your homework.
dig into this.
You did. We call ourselves the radishes, by the way. So our team mascot is a little radish in a spacesuit. It's fantastic. LASA loved it. They were like, oh my gosh, you have a team mascot. This is great.
Since we're on the subject of decision making, has any thought been gone into what sort of government will be required to construct these proposed bases?
That's a very, very good question and a very tricky question for sure, because I think this is hopefully where international collaboration comes into play. It needs to. It absolutely needs to. If it's just one entity, certainly so many things can be contingent upon that one government. And so if you have collaboration, by all means, there could be communication breakdowns and economic breakdowns as well. Maybe the water resource is more important to the US, but maybe not to the Italians, as an example. So this is where that communication would really need to come into play. And certainly technology as well. The Canadian Space Agency is doing some fantastic work on medical space exploration technology. And so how can we bring them better into the fold? South American space agencies are wanting to do more of science exploration. the Australian government is really hardcore into construction now. They're really excited into like the construction side. They have some laboratories that are getting into like the 3D printing of moon soil down there. It's fantastic, but we need to be better about like bringing everybody in to, I wouldn't say a single goal, because again, things can still horribly go wrong. And then if you feel like you failed with that one goal, it's going to be, how do you turn point your decision then, right? But if you give it as a overall objective of coming together, go to this area together, explore together, how do we share the data together? I think that in itself shouldn't really, hopefully, be contingent too much on government, although the funding will. So it's there whether we like it or not, as long as funding is there.
So does the ISS provide any good lessons for this?
Oh, absolutely, yes. So as far as communication and data sharing, and lessons learned from the Antarctica treaties as well, the International Space Station does have not exactly its own treaty per se, but we do have like MOUs through the UN that this is a shared international space outside of Earth, outside of any country jurisdiction, but every person up there is a representative of their country. So if they do anything wrong up there, they do have jurisdiction within their own country, kind of deal. That is put into place by the UN, by the way. I may or may not have looked up space murder. It's written, it's a policy, we want to be sure. But anyways, we have all sorts of policies in that regard. Yes, there are plenty of policies as far as international collaboration and communication goes on place. And so yes, that has been helpful, but there's still risks. There's always risks, which makes my job happy.
You mentioned MOU, Memoranda of Understanding.
Yes, thank you. All the acronyms, just tossing them out.
When it comes to civil engineering, there are such variability of differences that you have to invest into one solution or another. For example, what is possibly a form of basically construction of a community in the Sahara Desert will not work well in Antarctica and vice versa. So what point do we have to make a decision on where we go away from generalization to specialization, and how much of the climate variability of the moon will impact that decision?
Oh, very good question. So I'm not going to spoil it because there's a different team I'm working with that is working on that particular question. So yes, I was saying earlier though is that it shouldn't come down to aesthetics. It's got to be survival mode when it comes to design though, for sure. But what those safety protocols look like for every single building that you build for a specific purpose, it's going to have its own different protocol. So a chemistry lab is going to have a headache and a half of like, got to deal with ventilation. What about fire codes? What kind of chemicals are you going to have there? Is there going to be glass? What are you going to do with broken glass? And waste and so on and so forth. Versus simply just sleeping quarters. Okay, well, you're still going to have a ventilation type system, hopefully a fire suppression system as well. But you don't need to worry about, hopefully, need to worry about chemicals. Don't bring your chemistry lab into the bedroom. That should be a rule. Right. Don't bring your homework home. But just deal with it in the lab. But still, just in that design decision work though, yes, thankfully there's the international building codes. Can we adapt something like that for the moon and Mars? And so this is where some really fun conversations are coming about right now with another team I'm working with, as far as what can codes like that even work, and how do we put them into place? So implementation is another thing, policy involved with that. Certainly emergency protocols happen with that, monitoring as well need to be put into place. But with building codes, it's not like you need to worry about certain types of buildings either. You don't need to worry about grain silo type construction, because we're not going to be doing anything with grain, as far as I'm aware, on the moon. But nuclear power plants, energy grid systems, all of those require very specific volume and size and spatial awareness. Where are you going to build these? How efficient are they really going to be in the equator versus the polar region, and so on. So yeah, it's going to be a huge undertaking. We're not quite there yet, but the fact that we're talking about it right now is the fascinating part.
Dr. Ahrens,
Yes.
thank you so much. We'll wrap up now. I also want to thank our producer, J.D. Mack. So on behalf of the National Capital Area Skeptics, I'm Scott Snell saying so long from Bethesda, Maryland. We'll see you next time. Thank you again.
Thank
Bye-bye.
you.